Welcome everyone. First speaker of this session is Kuwari Mahanta from IIT Guwahati. She will talk about distance for curve in the curve graph of closed surfaces. Over to you.
Thank you. Hello everyone. Like the topic says, I'll be talking about curves which are at distance 4 apart in the curve graph of closed surfaces. This is a joint work with my advisor Sri Krishna. While preparing for this talk, I realized that these curves will also work for any finite type surfaces. So it's, the proof almost remains the same. So let's get on with a few notations. The first one would be that S subscript G would be a closed genus G surface for us. We'll consider our genuses to be at least 2, and here is a schematic of such a surface. Next, for us, curves would be simple closed curves, and which cannot be squished to a point. So if we look at the schematic here, our pink curves here, this will be curves for us, whereas the green ones won't be curves. Like we won't be considering them as curves. Next, if gamma is a curve on the surface SG, we'll take the square bracket of gamma to represent the isotopic class of gamma. So for example, the blue curves would represent 2 different isotopic classes, whereas the orange ones here belong to the same isotopic class. Also, henceforth, we'll be considering curves up to isotopy. Hence, with a slight abuse of notation, whenever the context is clear, we'll use gamma to denote both the curve as well as its isotopic class. Next, let's define the intersection number for 2 curves. So given any 2 curves alpha and beta, we denote the intersection number of alpha and beta as I of alpha and beta, and we define it as the minimum number of points in which any member out in the isotopic class of alpha intersects with any member in the isotopic class of beta. For example, if we consider 2 curves, the blue and the pink curve in S2, we see that they intersect at 5 points here, but we can find good isotopic curves belonging to the blue curve, that is isotopic to the blue curve and to the pink curve, which intersect just once. A recipe for doing this is that we just remove the bigons that are formed between these 2 curves, and we'll end up finding out the intersection number. And quoting Professor Menasco here, let bygones be bygones from here on. So as we have seen that like when we are considering curves up to isotopy, they can intersect arbitrarily high number of times. So, and because we'll be considering curves up to isotopy, I want my representatives to be nice enough. For this, what I do is that I define our next definition, which is minimally intersecting curves. I say that 2 curves, alpha and beta, are minimally intersecting if the number of points in which alpha and beta intersect is equal to the intersection number of alpha and beta. Henceforth, whenever I'm talking about any pair of curves, we'll consider that they are the minimal intersecting curves. So now comes the infamous mapping class group. So like it has already been defined, this is for any surface SG, it is the group of isotopic classes of orientation preserving homeomorphisms of SG. So suppose if one example of a trivial mapping class is that if you consider any surface SG and you take a arc on it and you just finger push the surface along that arc, we'll get a trivial homeomorphism, trivial mapping class of that surface. Another example is if we consider the S3 here and we just consider the action of rotating it by 180 degrees, like imagine barbecuing this surface about the central axis. So this gives us an order 2 mapping class in the genus in S3. And similarly, if we consider the 5 genus surface in this flower pattern and imagine rotating through its center by 2 pi by 5, we'll end up getting a order 5 mapping class. So these are a few finite order mapping classes. Let's try looking at a few, this class of infinite order mapping class. So the main class of infinite order mapping classes that we look at are known as Dane twists. Dane twists are defined for any genus G surface and for any curve on the surface. Here I will first define define Dane twist for a particular curve on a particular surface, and similarly, analogously, we can just generalize this. So if we consider S2 and the blue curve here, and we consider the action of twisting the surface about this green curve. Just hold the curve and give it a twist. That action is known as the Dane twist about the green curve. Another schematic way to imagine this is that cut the surface along the green curve, at one end give it a complete twist, and then just paste it back. And like this is one schematic of imagining the Dane twist, and we denoted this by T, and on the subscript we'll write the curve around which we are Dane twisting. A way to see that Dane twists are of infinite power is that look at the action of the Dane twist on the fundamental group of the surface. Next, let's look at how an easy recipe to obtain the image of a single curve under the Dane twist of another curve. So if I consider two curves alpha and beta, let's just look at the first the simple example on when alpha and beta intersect twice. So pink curve and consider this blue curve. The first step is we draw the two copies of beta that are parallel to each other, and each point of intersection of alpha and beta will have an image like this, where these are like just the parallel copies of beta here, and then at each point we perform this surgery, and performing this at each of the intersection point of alpha and beta will give us a closed curve, and this curve becomes the Dane twist of alpha about the curve beta. If we have alpha and beta intersecting at k number of times, instead of two copies of beta, we'll just draw k copies, and each of the intersection point will perform a similar surgery. So this is a quick recipe of obtaining how one single curve looks like under a Dane twist. So next, look at the main object of our interest. So the curve graph was introduced by William J. Harvey. He defined the vertices of the curve graph to be free isotopy classes of curves on SG, and he put an edge between any two vertex if they had disjoint representatives. That is, their intersection number comes out to be equal to 0. So for example, if we consider the vertices represented by this green, yellow, and blue curve, we see that they are disjoint, and hence we can put an edge between them. And because the pink and the yellow curve, they intersect twice with each other, we cannot put an edge between them. But we notice that we can find a path to the pink curve via this green vertex. This phenomenon is not just restricted to our pink and the yellow curve, but it generalizes to the entire curve graph, and we have the following theorem which states that the curve graph for any for g greater than or equal to 2 comes out to be a connected graph. Now we have a combinatorial object, and it's a connected graph, and we can equip it with the path matrix, which will transform it from the combinatorial object to a geometric object. So this gives us the leverage of doing geometry on the curve graph. So let's look at the geometry of this. Before we go into the geometry, let's look at a nice property where we link the geometry of the curve graph and the geometry of the surface. So the first definition we have here is that we say that two curves alpha and beta fill up the surface SG if, when we cut the surface SG along the two curves, we end up with components which are topological disks. For example, if I look at my blue and the pink curve here, this pair of curves were given by Thurston, and if I cut along these curves here, we'll end up with two octagons. One octagon I have tried components are start with one of the intersection point, just go here, and then you just keep on like just tracing the vertices here, the edges here, and we'll come back to our same place. So the property says that if we have two curves which fill up the surface, then their distance in the curve graph is at least 3. Intuitive proof for this property is that whenever two curves fill up the surface, whenever two curves don't fill up the surface, we'll always find an extra curve, say gamma, which is disjoint from alpha and beta. So moving on. So in the direction of the geometry of the curve graph, there is the seminal theorem which was given by Mazur and Minsky, who said that the curve graph comes out to be an infinite delta here is that once you have infinitely many such vertices that is adjacent to the one vertex, it becomes difficult that, okay, which path should I take now to calculate the distance from one point to the other. So basically that's why calculating distances in the curve graph becomes quite difficult. So if we move, so one of the question that fascinated us was, can we look at some good, nice enough, effective algorithm to calculate distances in the curve graph? So let's look at the narrative. So instead, so the first, so one of the quantities that is very much related to the distances in the curve graph is known as the minimal intersection number. So given any genus G and a distance n, we define I mean of Gn as the minimum of intersection number of any two curves on genus G which are at distance n apart from each other. So for example, if I take n is equal to 1, these are just disjoint curves, hence I mean of G1 comes out to be equal to 0. If I take n is equal to 2, then we can always find two curves which will intersect just once, and they will not, we can show that very easily that we can always find a curve that is disjoint from each other. Hence I mean of G2 will come out to be equal to 1. If distance is equal to 3, this is a nice result that was shown by Ogab and Taylor. They showed that for genus 2, this number comes out to be equal to 4, and for higher genuses, it comes out to be equal to 2g minus 1. The way they showed is that they used the collection of curves that were produced by Ogab and Huang, which intersect minimally in any genus G surface. These curves were given by Ogab and Huang as the form of in the form of a permutation that helps identify any two and gone, which when we identify, we'll just end up rediscovering our curves. So the next quantity that that we wanted to know was what is this value for n is equal to 4. As a bigger question, we were interested in finding out what is I mean of G comma n. Our interest was trying to use this quantity to find out some nice geodesics in the curve graph. So for genus G equal to 2, this value is known to be equal to 12. And this was given by Glenn, Manasco, Morrell, and Morse. They proved this value by using a software known as MICC. And for genus 3, it is only known that this is there is the upper bound 21. McGonigal proved this by producing an example, which are a pair of curves which are distance 4 apart and intersect 21 number of times. So it still remains open that what is the value for genus G greater than equal to 3. So before attempting to find the exact value, I wanted to see like, okay, how does these numbers interact with each other? So to see the numbers, I wanted to see a few pair of curves. And when I tried looking for this, I found that only a few pairs were known in the genus 2 surface and the genus 3 surface. For the genus 2, they were mostly given by Glenn Manasco's work. And we know one pair given by Hempel. And on S3, we had even lesser number of such curves. And for genus greater than equal to 4, we weren't able to find any such explicit examples which we could draw or see it as a graphic and how the numbers look like. So we went on the quest of finding what this value could be. So the way we went on is that we realized that the mapping class group acts via isometries on the curve graph. And we have the theorem by Dane and Licorice, which states that the mapping class group is generated by Dane twist about finitely many Dane twist about non-separating curves. So the question we asked ourselves was that how much does a single Dane twist displace one vertex of the curve graph from itself? So again, let's start with the simplest case. The first case we tackled was if alpha and gamma are at the distance 1 from each other, then how much is the replacement? We see here that there is no displacement, and the value remains as 0. If alpha and gamma are at distance 2 apart from each other, then we'll always find a curve beta, which is disjoint from alpha and gamma, and beta remains disjoint from alpha and T gamma of alpha as well. And hence we get that this value comes out to be equal to 2. The next question we ask is, what happens when the distance is equal to 3? This we were able to answer that if it comes out to be, if it is 3, then the displacement comes out to be equal to 4. Not only this, if we take any higher power Dane twist of alpha about gamma, the curves remain at distance 4 from alpha. So we will just try to see an application of this theorem to build distance 4 curves. Here we have taken a pair of curves which are at distance 3 in the curve graph. This pair of curves we have taken from the work of Ogab and Huang, where they gave the curves as the identification in the form of permutation of a 28 gon, and then we just identified them to recover this pair of curves, and we applied a theorem to get this pair of curves which intersects 49 number of times. So I'll just give a quick view, quick proof of for a single Dane twist, and then for higher power the proof is quite similar. So the way we'll prove is that we'll first show that this is bounded above by 4, and in the next half we'll show that this is bounded below by 4. For the upper bound, it's not difficult. So if we take a geodesic between alpha and gamma, and we apply T gamma, see gamma is equal to A3, so I've just written here TA3 here. I apply it to this geodesic. It's an isometry, so it will also remain as a geodesic. Now we notice that gamma or A3 is disjoint from A2. Hence, this vertex and this vertex are the same point. So this entire thing is they basically are the same curves. Hence, we can just like draw a path going from here and then going from here. So this gives us a distance 4 path between alpha and T gamma of alpha, and it's a path matrix. So this becomes that the distance here would be less than equal to 4. So we have an upper bound here. Now to show the lower bound, the strategy we'll follow is that if we consider this orange blob represents T gamma of alpha and take any curve which is at distance 1 from this curve, then if all of these curves are at distance 3 from alpha, then I'll have that T gamma of alpha will be at a distance at least 4 from alpha. But the main hindrance comes here is that here we'll have some infinitely many number of points that we need to check this criterion for. But comes to a rescue this theorem by Glenn, Menasco, Morrell, and Morse. I'll not go into the theorem, but roughly what the theorem says is that if I can show that my T gamma of alpha and alpha fill the surface, then I need to check this greater than equal to 3 property for only a finite subset of the one ball of T gamma of alpha. And this, the curves belonging to this subset are very nice curves which help us get the proof done. So apply again. So the first step is showing that the curves alpha and T gamma of alpha are distance at least 3. Again, I will show the proof for this nice pair of curves. For any other pair of curves, the proof follows similarly. Like recall that we had the property that they are at a distance at least 3 if and only if they fill up the surface. The strategy we'll follow is that we'll try to show that alpha and T gamma of alpha fill up the surface. So if alpha is the pink curve and gamma is the blue curve, the way we tried creating T gamma of alpha is that the first step we tried drawing k copies of gamma. That is, for here, since the intersection number is 4, there will be 4 copies of gamma here. Next, we see that the surgery that turned those the 4 copies into T gamma of alpha is restricted to this annular neighborhood of alpha. So to obtain the components of T gamma of alpha and alpha, it's basically each component will have a part in outside this annular neighborhood and a part that lies in this annular neighborhood. So if we look at what lies outside the annular neighborhood, we see that these are basically just disks and rectangles. How do we see that? Because gamma and alpha fills, and these are just parallel copies of gamma, we have the main octagons here, and here, because of the 4 copies, we'll have a few rectangles. So outside the annular neighborhood, we have now just disks. In the annular neighborhood, let's look at what happens. Because of the surgery, we'll have that each of the rectangles that's present here, it gets replaced by another rectangle. So when we try to get back our components, we are basically replacing our rectangles by rectangles. Hence, our components, our topological disks remained as disks, and hence we get that the alpha and T gamma of alpha fill up the surface. Now the part comes of the second one, where we have to show that for the nice enough set of green blobs, we have to show that this is at distance 3 from alpha. Again, we'll have the strategy that if delta is a curve that lies at distance 1 from T gamma of alpha, delta and alpha fills. Here is a view of the annular neighborhood of gamma. The central curve is gamma. And the thing we want to notice here is that the presence of the arcs of T gamma of alpha, they are present in this nice spiral pattern. So because of this, what it does, it forces any arc of delta to go around the entire annular neighborhood in a spiral pattern. So these are the only two possibilities that we can get if we try to nicely isotope the curves. And so if I look at one of the possibilities, I see that it starts from one of the rectangular disks and it goes around and it comes back. Barring this rectangle, what happens is in each of these rectangles, the arc of delta is parallel to the arc of gamma in that. So at this point, if I imagine my surface SG cut along alpha, wherever I have an arc of gamma in that, I am going to get an arc of delta there, just parallel to it, except for this arc. If now these two components belong to two different components of SG cut along alpha and gamma, then I do not need any delta arc here. I will still end up having components of the components are topological disks. But if they belong to the same component, and when we I'll need something to cover this the filling property of this gamma arc. But I see that if I glue along this and the surface is cut along every other alpha arc and every other gamma arc, then I'm left with just an annulus. But because of the way this gamma arc is present, it will go from one of the boundary component to the other, hence cutting up the annulus. This will give us that that delta fills up along with alpha. So we have so one of the corollary we have from this theorem is that I min of g comma 4 is bounded above by 2g minus 1 whole square. The way to prove is that just consider two curves alpha and gamma that intersect minimally, which is equal to 2g minus 1, proved by Augab and Taylor. And because of because of this formula, it comes out to be equal to 2g minus 1 whole square. So I still have, okay. Next, the next project, I tried extending this from distance 3 and 4 to distance 4 and 5. And I just give you the one example that I found. So here, by taking alpha and gamma to be distance 4, they are minimally intersecting. And these pair of curves were given by Berman, Margalit, and Menasco. And if I take the Dane twist of alpha about the curve gamma, what I get is that these curves come out to be equal to distance 5. Which is a nice way of extending our theorem from the previous work, but it doesn't work in general. So here I have just the geodesic between the two curves. Like I can see here, if you look at it, that B0 and B1 are not intersecting, and they are all mutually, if you take consecutive vertices, they are disjoint from each other. So here I have B3 and B4, which will be a component of the geodesic. They are again not disjoint from they are disjoint from each other. And one of the easy corollary of this is that the I min of 2 comma 5 will be bounded above by 144. So the conclusion here is that okay, so another theorem, another observation here is that instead of taking just T gamma of alpha, if I take, there will exist a very high power Dane twist of alpha about the curve gamma, where this distance starts becoming 6, which is different from our previous theorem where it was 4 all around. So a conclusion from here we can draw is that the rectangular components of the curve start having an impact on distances in the curve graph. So one of the questions that I have in mind is that, is there a surgery of curves which will help us reduce these rectangles, yet keeping the distances the same? So also because these two curves are minimally intersecting at distance 4, The next one of the next question I have is that if two curves are minimally intersecting, will this distance always come out to be equal to 5? Because once the rectangles start increasing, I know that this distance will start becoming 6. And another one is that will I mean of g comma 5 be bounded above by the square of I mean of g comma 4?
Is there any question or comments?
Once you draw it, it's not difficult to draw the Dane twist because you just keep copying the arcs and then you do the surgery. Basically, what you do in real life, you do it in, I'll show you maybe here. So once you draw these arcs, you just copy it and each point you do the surgery. So. I have not checked that. Okay, so for this case, the geodesics come out to be efficient, which are the geodesics considered by Berman, Margalit, and Manasco. Yeah. Sorry. Yeah, I can do that for n actually. So it's the same trick that I did. So if alpha and gamma are at distance n, then alpha and t gamma of alpha, or you can take any power, comes out to be less than 2n minus 2. You'll just do that one node, you will just, that shaping. For any alpha and gamma you take to be at distance 4 apart, it will be 6. No. For any distance 4 you take, you'll be able to find some high enough power of Dane twist for which this comes. Yeah. So if alpha and it might change. So yeah, this I actually don't. Theoretically, it might become maybe 1 is 2, 1 is 3. But then again, I don't know because the constant here is only about existence. So we used an argument that was given by Agab and Taylor. So there exists some B they show using subsurface projection arguments. So using that, yeah, you can build this up. You will not go more than 2n minus 2. Is that what you're asking?
I'm asking equally. You have this formula for like 2 cases.
Yeah.
Where it's 4 and 6 and 3 and 4.
Mm-hmm.
You have a conjecture
For n, no, because that's the conjecture I wanted to test for the next one, but I couldn't prove it for all the curves. So this is just one particular example. So the main result was that all 4, 5, and 6 can happen. So I give a theorem which says that, okay, for this kind of curves, maybe it'll be 5 and 6, but exactly when, I don't know. Yeah, this argument works for any alpha gamma, but so yeah, I hope that answers. Yeah.
Like alpha gamma have distance 4. We twist around gamma, you have distance 5. Twist alpha around gamma alpha, get 6.
Yeah, a similar result was I think done by Ogawa and Taylor, who produced bi-infinite geodesy, but they took very particular curves like A0 and A3, and they kept on Dane twisting one about the other, and they got this one. But the thing with their result is that there exists a constant. So like at what power does it become this distance is, yeah. So, but here I have 5, but then they'll say, okay, there will exist a power on which if I take instead of gamma, another there's a curve, and there exists a constant in which it will become 6. But what is that constant like?
Any more question? No more question. Let's.
Thank you.